Imagine you have a long text in a shorter pattern, and you need to find every place the pattern appears within the text. For example, finding ABC in. The naive approach compares the pattern at every single position, which can take a long time, roughly O and M operations. But what if we could do much better perhaps in O and plus M time? Let's explore a powerful tool called the Z-array. For any string S, Z, I tells us the length of the longest substring starting at index I, that is also a prefix of S. For example, in aabxaa, Z, 1 is 1 because a matches the prefix a. Z, 4 is 2 because a matches the prefix a. By calculating this for every position, we gain valuable information about the string structure. Let's manually compute the Z-array for S equals aabxaa. Z0 is conventionally the length of the string. For I equals 1, a matches the prefix a, so Z1 equals 1. For I equals 2, b does not match the prefix a, so Z squared equals 0. Similarly, Z cubed equals 0. For I equals 4, a matches the prefix a, so Z4 equals 2. And for I equals 5, a matches the prefix a, so Z5 equals 1. Now for the clever part, the Z-box optimization. We maintain a Z-box defined by a, l, r interval representing the rightmost substring that matches a prefix. If our current index I falls within this Z-box, we can use the Z value of its mirror index il to potentially speed up the calculation of Z, I, avoiding redundant character comparisons. Can we use this for pattern matching? We construct a new string by concatenating the pattern. A special separator character like $, and the text p plus $, plus t for abc, and xxxxabcxxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxabcxabcxabcxabcxxabcxabcxabcxabcxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcxxabcx string. We look for position I where zi equals the length of the original pattern, p. In our example, abc equals 3, the length or abc. It signifies that the pattern ABC stood at that position in the original text. Z algorithm, with its Z-box optimization, achieves a remarkable linear time complexity of O, n plus m, where n is the length of the text and m is the length of the pattern. This is a significant improvement over the naive O and M approach, making it highly efficient for string matching tasks.